Hello friends, so this is part 3 of the questions that were asked in the year 2019, and in this we are going to solve 12 questions from the 2019 mains. Some of the questions of mains and advanced are still left, so which we'll be covering in the part 4, and hopefully that will be the last part from this 2019 questions. So in the first question, it states that a simple pendulum of length L is placed between the plates of a parallel plate capacitor having electric field E as shown in the figure. Its bob have a mass m, charge q. The time period of the pendulum is given by. A basic figure is given to us. We have a parallel plate and our left side is positive and the right side is negative, and charge is also positive. So this bob will be attracted towards the, you can say, right side, because of the electric field everything is on towards that. So in this case there will be two forces that will be acting. One will be the gravitational force, let us suppose we call that Fg, which will be equal to over mg, and it will be acting in the downward direction. And there will be second force, we can call that electric force, let us suppose that is given as Fe, and that will be towards our right and will be charge multiplied by the electric field. And so there will be two forces that will be acting on the mass m. So we are only interested in the forces. So this is mass m. In the downward direction we are going to have our mg, and towards right we are going to have our Fe, which we called as q multiplied by E. Okay. And mg will be in the downward direction, and which is our gravitational force, that is our Fg. So in terms of now here both the forces, our Fe is perpendicular to our Fg. So from here we can say that our net force, so we can just draw our Fe and our mg, sorry, not mg but Fg. Therefore the net force we can easily find out, and that will be something like this. Suppose this is our F net. Okay. So you can say in terms of our, let me write this in the form of coordinate, and this is our x-axis and this is our y-axis. So this will be our I unit vector and this will be our minus j. So we can say that our F effective, F net will be equal to our Fg plus Fe, and we can easily substitute the values, and F net will be giving us acceleration. So we can say that our mass into our net acceleration will be equal to our, this will be our mg plus, and we can say this will be our QE multiplied by I. And we are mainly interested in the magnitude part. Okay, direction doesn't matter, so we are going to just ignore this part, and we can say that our net acceleration will be equal to G, and this comes as plus QE divided by M. It means from here we can, or let us put here negative, we are, and later on we can just find out its magnitude, much more convenient. So from here we can find out its magnitude. So we can say net acceleration will be equal to our G square plus QE upon M and whole square and its square root. And we already know the formula for the standard pendulum, that is a time period A is equal to 2 pi square root of our length divided by A acceleration net and its magnitude. We substitute it, we get this as 2 pi, and L upon G square plus QEM and whole square and its square root. So we get option number A is the correct one. Option A is correct. Next question. It states that figure shows charge Q versus voltage V, graph for series parallel combination of the two capacitors. The capacitances are. So basic graph is given to us. We are having, you can say, two plots, one is A and another one is B. They are having same voltage, but the charge on A is given as 500 microcoulomb and charge on B is given as 80 microcoulomb. Okay, both are having same, you can say, voltage source. And the basic formula for the charge is our Q is equal to C multiplied by V. Okay. So which basically means that slope with the graph of that the slope is going to give us a capacitance. From here we can say slope of graph gives the capacitance. Okay. Slope of the graph gives us capacitance, and like you said, there is a series and parallel combination. So from the slope we can identify, or we can make a wild guess that which of graph, whether A or B, will be representing a series or which of will be the parallel. And from the slope itself, we can say that slope will be more for parallel combination. Slope will be more for parallel combination. And so it means this CA, the A will be representing as parallel and this B will be representing as a series. Okay, let us suppose we have two capacitors C1 and C2. Therefore, because in the question it is mentioned that we are having two capacitors, so we say for two capacitors, C1 and C2, for parallel, we can say the resultant will be C1 plus C2, and that is nothing but our charge oblique voltage, and charge for parallel is our 500 and voltage our 10 volt, and this 500 microcoulomb, so 10 is power minus 6, so this comes as 50 into 10 is power minus 6. So let me write it here. So from the parallel we get C1 plus C2 is equal to 50 into 10 is power minus 6. And for series, we get this as C1 C2 divided by C1 plus C2 is equal to charge oblique voltage. For series the charge is about 80 microcoulomb, so this comes 80 into 10 to the power minus 6 divided by 10, which comes as 8 into 10 to the power minus 6. And we already know our C1 plus C2, so we substitute it here. We get C1 times C2 is equal to C1 plus C2 into 8 into 10 to the power minus 6, which comes as 50 into 10 to the power minus 6 times our 8 into 10 to the power minus 6. And we get that our C1 times C2 will be equal to, this comes as 400 into 10 to the power minus 12, and C1 plus C2 is our 50 into 10 to the power minus 6. And here we can just solve them. We can take C1 will be equal to 400 divided by C2 into 10 to the power minus 12. Substitute here, we get this as 400, and okay, I think it is much more better option. One second, this is our C1 times C2. Okay, so much better option is to make a wild guess from the options that are given to us. Okay, so we are given that C1 plus C2 should be equal to 50, and C1 into C2 must be equal to our 400. Okay, and that is only possible for this particular, because for C1 plus C2 is equal to 50, So we are having only C and D is our summation. The product is only true for D. So option D is the correct. This is a much better option. Otherwise it will be becoming quadratic and it will be lengthy to solve. Therefore we can say our C1 will be equal to 10 microfarad and C2 will be equal to 42 microfarad. So option D is correct. Option D is correct. Next question. We are given the parallel combination of two air-filled parallel plate capacitors of capacitance C and NC are connected to a battery of voltage V. When the capacitors are fully charged, the battery is removed, and after that, dielectric material of dielectric constant K is placed between the two plates of first capacitor. The new potential difference of the combined system will be. So here we are given that we have parallel combination of two capacitors. So we can just, you can say, draw this circuit into two conditions. First condition is without dielectric, and we have two capacitors. One is our C and another one is our NC, and both are in parallel connected to a voltage source, and that voltage source is given as V. And after some time it says that when they are fully charged, this voltage source is disconnected, and you can say a dielectric is introduced between the first capacitor. It means on C dielectric is inserted, and so circuit will be coming something like this, and here dielectric inserted and the second one is without dielectric. So this is NC and voltage will be our V, and here dielectric constant is given as K, so the capacitance become our Kc, and voltage is our V. So therefore let us independently call them C1, C2. So this will be C1 and this will be our C2. So this is our initial condition and this is our final condition. And let's find out the amount of charge in the initial condition. So we say initial condition charge on C1 let us call that as Q1, which will be equal to C multiplied by voltage source V, and charge on C2 let us call that as Q2. Q2 will be NC multiplied by V. We can find out our total charge. Total charge, and this is our Qt, will be equal to Q1 plus Q2. So this comes as CV plus NC times V. So we can write our Qt is equal to CV, we can take common, and this comes as 1 plus N. So this is the total charge initially. And Now after the battery is removed, the total charge will remain conserved. Okay, so you can say final condition. Final condition, which basically means battery is removed. So first thing will be that total charge is conserved. We can say charge is conserved. Charge is conserved. And new capacitance for the first one, that is C1, that was called C1. So we can say that dielectric is inserted in capacitance capacitor 1. Therefore, new capacitance let us call this as C1 prime will be equal to K times C1, and this comes as K times C. Okay, let us call this as C1 prime. And for this capacitor 2, that will be same. Capacitance for C2, that will be N times C. Okay. Now we can find out the new equivalent capacitance. We can say final equivalent capacitance we get C equivalent prime will be equal to our Kc plus N times C, which comes as which comes as C K plus N. And we are going to find out so we get new capacitance will be equal to Ck plus N, and we can find out that new common potential, or we can say final common potential. Final common potential, let us call that V prime, and the charge will be conserved, so therefore charge will be our Q total Qt, and new equivalent capacitance, that is C equivalent. So we get our V prime will be equal to Q total was our 1 plus N C multiplied by V, and C prime we found out as C is equal to K plus N. Here C and C cancel out, so we get our new potential is equal to 1 plus N times V and divided by K plus N. So the option that is correct is 1 plus N, and option number A is the correct one. Option A is correct. Next question. It says that a capacitor with a capacitance of 5 microfarad is charged to 5 microcoulomb. If the plates are pulled apart to reduce the capacitance to 2 microfarad, how much work is done? So we are given that we can once again draw approximate figure for initial and final condition. So we have initial condition, capacitance is C1, which is given as 5 microfarad, and the charge is our 5 microcoulomb, and finally it states that the plates are pulled together. Let us suppose a little bit plates are further, and it says that our C2 is our 2 microfarad. Okay, and there is no external battery source of some kind of, therefore the charge will be conserved. So this our Q2 will be equal to a Q1, which is our 5 microcoulomb. In most of the questions for this capacitance and something like that, this charge plays an important part. Okay, most of the questions which we have solved so far, directly or indirectly, we observe that the charge is always conserved. Okay. So we can just find out the initial energy, final energy, and we can get the work done. So we can find out the initial energy. Let's suppose that is a U1, which will be equal to our Q square divided by our 2C, and Q is our 5 microcoulomb, and this is C1, Q1, and we have this as 5 into 10 to the power minus 6 whole square divided by 2 into 5 into 10 to the power minus 6, and we get that our U1 is equal to 2.5 into 10 to the power minus 6 joules. Similarly, we can find out our U2. U2 will be equal to Q2 square divided by twice C2. Charge is same, that is 5 into 10 to the power minus 6 whole square divided by 2 into 2 into 10 to the power minus 6. So we get our U2 will be equal to, this will be coming as 6.25 into 10 to the power minus 6 joules. Work done is difference between the energy. So we can say work done which will be nothing but our W is equal to U2 minus U1. U2 is our 6.25 minus 2.5 10 to the power minus 6. So we get our work done W is equal to 3.75 into 10 to the power minus 6 joules. So this comes as 3.75. Option number D is the correct one. Option D is correct. Next question. We are given that a parallel plate capacitor has 1 microfarad capacitance. One of its two plates is given plus 2 microcoulomb charge and other plate is given as 4 microcoulomb charge. The potential difference developed across the capacitor is. So in this case, we are given a parallel plate capacitor and it says that one plate, suppose our left side plate is having a 2 microcoulomb charge and our right side plate is having a 4 microcoulomb charge, and we have to find out the potential difference between the two. That is our V. And capacitance is given to us as 1 microfarad. So first of all, we have to find out what will be the net charge. Okay, because standard formula we already know, which is V is equal to Q upon C. And this Q charge is either on the first plate or it is on the second plate. Okay, but here it has to be same. But here it is different, plus 2 microcoulomb and 4 microcoulomb, plus 4 microcoulomb. Okay. So therefore, we have to find out in order to this our potential, that is our potential difference, that is our V is equal to Q upon C, and we have to find out the value of this Q. Okay. And in parallel plate capacitor, we have to remember that these two plates should be having equal and opposite charge. Okay, so this first one is a plus and second one is going to have minus. So let me write that for parallel plate capacitor, two plates must have equal and opposite charge. Equal and opposite charge. And this equal and opposite charge results in our electric field, and potential difference, and thus potential difference, potential difference. Now in this case, we are given that both you can say the plates are positively charged, but if you look closely, one plate should be having ideally plus Q, other one is going to have minus Q. So this net charge on both the plates is equal to 0. Okay. But in this case, it is non-zero. So we have to find out the net effect on the capacitor, how this it is going to behave. Therefore, we are going to find out the effective charge contributing towards the electric field and potential difference. Effective charge contributing to the electric field and potential difference. and let us suppose that effective charge is our Q. So we can write this Q will be equal to our 4 minus 2 and divided by 2, which comes as obviously microcoulomb, which comes as 1 microcoulomb. Now we can easily find out the potential difference, that is our V. So we can say our V will be equal to Q upon C, and Q is our 1 microcoulomb and capacitance is also given as 1 microfarad. This gives us 1 volt. Okay. So option number A is the correct one. Option A is correct. A is correct. And we can just also make a wild guess of the values of the charges, and that wild guess can be made on the basis of your charge induction. If we are having two plates, then on the inner side of these plates, okay, on the inner side, the charges will be always equal and opposite. So in the first case, if suppose on the our left side, if there is a charge of minus Q, then on the right side, inner side, it has to be plus Q, and the remaining charge will be redistributed on the external side. Okay. So we are given here 2 microcoulomb and this is our 4 microcoulomb. So from the inner side, we are very clear that the charges has to be same and opposite because of the induction process, and the rest of the charge will be redistributed at the, you can say, on the outside. Okay. And so based on this, we know that the let me draw this here. So if let us draw this is a little bit thicker one. So this is a plate 1 and this is a plate 2, and on the inner side, let us suppose this is our minus Q and here it will be our plus Q, and rest of the charge will be distributed on the outer side. Let us call this as QA and let us call this as QB. They can be same and they can be different. And here we are given as plus 2 microcoulomb and this is given as plus 4 microcoulomb. Okay. So this summation of both should be equal to plus 2, and here the summation of both the charges should be equal to plus 4. Okay. So based on this, we can also come to a conclusion that this minus will be equal to over minus of 1. This will be plus of 1, and this QA will be coming as 3 and QB will be coming also as 3. Okay, so this we can also make a, based on this we can find out the net charge on this, and we are going to get the same answer. Okay. Next question. It states that the voltage rating of a parallel plate capacitor is 500 volt. Its dielectric can withstand a maximum electric field of 10 to the power 6 volt per meter. The plate area is 10 to the power minus 4 meter square. What is the dielectric constant if the capacitance is 15 picofarad? And this question is more or less directly related to the formula. We already know that capacitance of parallel plate capacitor with dielectric capacitance of parallel plate capacitor with dielectric let us suppose that is given as C, and this C will be equal to K, dielectric constant, epsilon naught, that is A, and divided by D. And we are supposed to find out the dielectric constant. Electric field also given to us, so we also know that our electric field between the plates capacitor, that is E, is equal to V upon D. And in this capacitance equation we have to find out this particular D, which we are going to get from this equation. So we can say our D is equal to V upon E, and it is given as 500 volt and divided by 10 to the power 6. So we get distance D is equal to 5 into 10 to the power minus 4 meters. Now we can straightforward find out our dielectric constant. So we can say our C is equal to K epsilon naught A upon D, which gives us that K is equal to C times D epsilon naught A. And C is given as 15 picofarad, 10 to the power minus 12, and D we found out is 5 into 10 to the power minus 4. Epsilon naught we know is our 8.86 into 10 to the power minus 12, and area is given to us 10 to the power minus 4. So this gives us that value of K, dielectric constant, will be approximately equal to 8.5. So option number B is the correct one. B is correct. Next question. And it states that in the circuit shown, find C if the effective capacitance of the whole circuit is to be 0.5 microfarad. All the values in the circuit are in microfarad. So we are given this circuit, and it says that its equivalent capacitance is our 0.5 microfarad, and we need to find out the value of C. So we are going to solve these individual capacitances. So from here we can see that this value of 2 and 2, these are in parallel, and these 2 and 2 are in series. Okay. So we can just redraw the circuit, and this is our value of C. Here we are having 2, and this will be giving us one capacitance, that will be like this, and here also we are going to get one single capacitor, and this will be our point A, and this is our point B. Okay. And let us call this as C1 and this combination as C2. So this is our C2 1, and here we have 2, so this combination will be coming as C2, this combination will be coming as C1. And our C1, because both of them are series, so this will be coming as 2 into 2 divided by 2 plus 2, so this comes as 1. Similarly, we can find out our C2. C2 is parallel combination of both, so this comes as 2 plus 2 is equal to 4. So we have this as 4 and this as 1. And once again, these 2 will be coming in series and this will be coming in parallel. So let us call this as our C3 and let us call this as C4. So we can draw an individual circuit, and this is our 2, and now we are having this as our C4, and here we are having this combination as C3. This is our 2C, point A and point B. So C4 is a parallel combination of 1 plus 1. So we can write our C4 will be 1 plus 1, that is equal to 2. So this comes as 2, and we can write our C3, which is a series combination of 2 and 4, and the series combination of 2 and 4 will be coming as 2 into 4, and this is 2 plus 4, which comes as 8 upon 6, giving us 4 upon 3. So this comes as 4 upon 3. And further, these two will be in series, and let us call this as our C5. So we can further draw the circuit. We have our C3, and that will be our C5, and this is our point B, and this is our C5, which is a series combination of 2 and 2. So therefore we can say our C5 will be equal to, this comes as 2 into 2 divided by 2 plus 2, which is 4 and coming as 1. So this is 1, and C3 we found out is our 4 by 3. This is C and this is point A. And we are having that these two will be in parallel with each other. Let us call this equivalent as C6. So we can just redraw the figure. So this will be C, and this will be over C6. This is C, point A, as well as point B. So we can say our C6 is parallel combination of 4 by 3 plus 1, which comes as 7 by 4. So this comes as 7 by 4. And these two are in series, and this equivalent is value is given to us, and that value is 0.5. Let us suppose this is our C7. So we can just draw one capacitor now. Its value will be our C7, C7, and it is given as 0.5. This is between A and B. So we can say our C7 is equal to, this will be C multiplied by both on series, C6 divided by C plus C6. And C6 is our 7 by 4. So this comes as 7 by 4 times C, and this will be C plus 7 by 4. C7 is our 0.5. So we can just solve it. We cross multiply it. We get this as 7 by 4. 7 by 3. By 3, and this is our 7 by 3, and this is also 7 by 3. So we get this as 7 by 3 times C is equal to 0.5 multiplied by C plus 7 by 3 times 0.5. And we can just easily solve it now. We take C as common, so this comes as 7 by 3, and this will be our minus 0.5 is equal to, this comes as 3.5 divided by 3, and this gives us that our C hopefully it is, and we can take LCM, that is our 7 minus 1.5 divided by 3, and is equal to 3.5 divided by 3. 3 and 3 cancels away, so we get that value of C will be equal to 3.5 divided by this comes as 5.5. 5.5, or we can write this as 35 divided by 55, and we can write this as goes by 11 and this goes by 7. So we get our C is equal to 7 by 11. That is our requirement, that is 7 by 11 microfarad, that is D is the correct one. This is our microfarad. Option D is correct. Next question. It states that a parallel plate capacitor with plates of area 1 meter square each are in separation of 0.1 meter. If the electric field between the plates is 100 Newton per coulomb, the magnitude of the charge on each plate is. So in this case, we are given that electric field is given to us and we have to find out the charge on each plate. Its area and separation is given to us. So first of all, we are going to find out the surface charge density. Okay. And we can say surface charge density. Let us suppose that you have sigma, and this sigma is equal to our electric field multiplied by epsilon naught. Value of electric field is given to us, so we can say our sigma is equal to electric field is of 100. Epsilon naught is a standard value. We know that its value is our 8.85 into 10 to the power minus 12. So this gives that the value of sigma is our 8.85 into 10 to the power minus 10. So we are able to find out the surface charge density. And now we are going to use this surface charge density, or we know the surface charge density is equal to charge per unit area, and from there we are going to find out the charge. So we can say that our sigma is equal to charge per unit area. From here we can say our charge is equal to sigma multiplied by A, and this comes as 8.85 into 10 to the power minus 10. Area is given to us as 1 meter square, so this comes as 1. So we get our charge Q is equal to 8.85 into 10 to the power minus 10 coulombs. So it comes as option B is the correct one. Option B is correct. Next question. The charge on a capacitor plate in a circuit as a function of time is shown in the figure. What is the value of current at t is equal to 4 seconds? So basically, relationship between the charge and the time is given in with respect to the graph, and we have to find out the value of the current at t is equal to 4 seconds, which is this value. And we know that our current, that is our I, is equal to rate of charge dq by dt, rate of change of charge with respect to time. And we can also say that the slope of the graph between the charge and time represents the current. You can say slope represents the current. and we need to find out the slope at t is equal to 0, t is equal to 4. We can see at t is equal to 4 seconds, we can clearly see that the slope is 0. Slope of the graph is 0. Therefore, the current or dq by dt, so we can say from here that our dq by dt will be equal to 0, or we can say our I is equal to 0. So option number C is the correct one. C is correct. Next question. It states that in the figure, after the switch S is turned from position A to position B, the energy dissipated in the circuit in terms of capacitance C and the total charge Q is. Basic circuit is given to us. Initially, switch S is at position A, then the capacitor, let us call this as C1. This capacitor is our C2. So C1 is connected to the battery EMF E. In the second part, the switch is pushed to our B, and we have to find out how much charge will energy will be dissipated. So we are going to find energy, initial energy as well as the final energy. So let's find out the initial energy when the position of the switch is at A. And for that, we can just draw an approximate figure. So this is our position A, and this is our switch, and EMF E, C1 is our C. So let us assume that the charge on capacitor C is our Q. So we can say initial energy stored. Initial energy stored. So we can say the charge is, let us suppose, Q, and we can say our U initial, UI, will be equal to our Q square upon 2 C1. C1 is our C, so this comes as Q square upon 2C. And when the switch is moved to position B, so we can just draw the circuit now. So this is position B, and we have capacitance whose value is 3C. We called it C2, and this is C1, capacitance is C. Now initially C2 is uncharged. Okay. So final condition, means switch is at B. Switch is at B, and initially C2 is uncharged. So we can say C2 is uncharged, and the charge was on our C1 was Q. So this Q will be redistributed among C1 and C2. Okay. So let's find out first of all the equivalent capacitance. So we can say the two capacitors are connected in parallel. One second, let me, this is our A, and this is our EMF. Okay, and here also, let me complete the circuit. This is our C2 and this is position B. Okay, EMF is E. So our C1 and C2 are in parallel. C1 and C2 are in parallel. Therefore, we can say that C equivalent will be equal to C1 plus C2, which comes as C plus 3C, giving us 4C. And this charge Q will be spread on this equivalent capacitance, which we just found out is our C equivalent, and this C equivalent is going to have a charge of our Q. So we can find out that new potential, common voltage, because they will be charge shifting and they will be having the common potential. Therefore, we can say the total charge which is our Q is now spread across C equivalent, which is nothing but our 4C. Therefore, from here we can find out the common voltage, which is our V, will be equal to our Q divided by 4 times C. So we can find out the final energy. Let us call that a U final, will be equal to our half CV square plus, and this comes as half 3V square, 3C, sorry. Okay, so it means energy because of the C1 and energy because of our C2. So we get our U final will be equal to, we can just write in the form of charge. So this comes as our 1 by 2, and we C plus 3C, V square we can take common, and V square is our, this comes half, and we have this as 4 times C, and V is our Q square upon this comes as 16 C square, and here 16 goes by 4 and square goes by C, so we are left with our half, and this is our 8. So you can say this will be 1 by 8 Q square upon C. Yeah, now we are going to find out work done, energy dissipated. So we can say energy dissipated let us call that delta U will be equal to initial minus final, U initial minus U final. So we know that this delta of U initial is our Q square upon 2C. So this comes half Q square upon C minus this comes as 1 by 8 Q square upon C, and 8 will be our LCM. So this comes as a 4 minus 1 and Q square upon C. So this comes as 3 by 8 Q square upon C. Delta U is equal to 3 by 8 Q square upon C. So option number D is the correct one. Option D is correct. Next question. We are given that in the figure below, the charge on the left plate of 10 microfarad capacitor is minus 30 microcoulomb. The charge on the right plate of 6 microfarad capacitor is. So we are given charge on the left plate of 10 microfarad and we need to find out the charge on the right plate of 6 microfarad. And this we have to find out. And we can just think it like this, that initially we provide a charge on this 10 microfarad of 30 microcoulomb. And then it is connected to the circuit. So this 30 microcoulomb will redistribute itself. Okay, that's a basic premise of that, and this 30 microcoulomb is going to remain constant. Okay. So we can just draw the circuit a little bit different way, because the charge is given on the left plate. Okay, and the left plate is minus 30 microcoulomb. Okay, so let us, so this is our 10 microfarad and there are two capacitances, and here we have our 6 microfarad and the other one is our 4 microfarad, and charge on the left is given as minus 30. So obviously on the right it has to be same but with the opposite sign. And for this 30 microcoulomb charge will be distributed among our 6 microfarad, and that we require on the right side. Okay, so this is a 6 microfarad and this is our 4 microfarad. So this will be our distributed something like this. Okay. In the shorter version we can say, because the left and right is only going to give us a sign, magnitude will be same. Like in 10 microfarad, we can draw a conclusion that the charge on this is our 30 microfarad. So microcoulomb, not farad. So magnitude is our 30, left and right there will be positive and negative. Similarly, we can assume that on 6, let us suppose we are having a charge of Q1 and 4 we are having a charge of Q2. So on the left and right it will be plus and minus, that will be only difference, the magnitude will be same. Okay. And here this 6 and 4 are connected in parallel. Okay. So it means if they are connected in parallel, let's call them this our C1, let us call this as C2 and this as our C3. So we can say C2 and C3 are connected in parallel. C2 and C3 are in parallel. So which basically means if they are in parallel, they are going to have the voltage across each capacitor will be same. You can say that voltage across each capacitor will be same. And let us suppose that voltage over V. So we are having voltage V here as well as here also. And like I said, the charge on C2 is our Q1 and charge on C3 is our Q2. But because of the conservation, this Q1 plus Q2 should be equal to our 30 microcoulomb. Due to charge conservation, Q1 plus Q2 should be equal to our, that is given as 30 microcoulomb. Or in simpler terms, we can also say that if they are equivalent, they are in parallel, and they are equivalent, if we call this as, let us suppose C, let us call this as C, and we can just draw the equivalent circuit. So this is our C1, this is our C, and this final one, let us call this as C1, 2, 3 and 4. So this is our C4. So this is our C4. So all these capacitors are in series. C1, C and C4 are in series. Therefore, each one of them is going to have same charge. Okay. So we are going to have 30 microcoulomb here. C is also going to have 30 microcoulomb, and C4 is also going to have a 30 microcoulomb. And the C is a parallel combination of C2 and C3. C2 and C3. So this total charge on this C2 and C3 will be equal to 30 microcoulomb. And like I said, that the voltage of C2 should be equal to voltage of C3. You can say that voltage at C2 will be equal to voltage at C3. So in terms of capacitor, we can say that our Q1 upon 6 is equal to Q2 upon 4. And we are having two equations, and we can easily find out our Q1 and Q2. Okay. So let us suppose this is our equation 1 and this is our equation 2. So you can say from equation 1 and 2, equation 1 and 2, we can say that we are only interested in our Q1, so we are going to find out only Q1. Therefore, we can write that Q2 is equal to 30 minus Q1, and we get this as our Q1 upon 6 is equal to 30 minus Q1 upon 4. Now it is simple, we can just sort it out, and we get this as 4Q1 is equal to 180 minus 6Q1, and this comes as 10Q1 is equal to 180. So this gives us that our Q1 is equal to 18. So it means that the charge on this we call this as C2. Charge on C2, which was our Q1, is equal to our 18 microcoulomb. And we know that the left plate was given as minus 30. So right plate will be our plus 30. Therefore, our this we are supposed to find out right or left on the right plate of C1. So right plate of C1 will be giving us, because this will be plus, so we are going to get this will be minus 18 and this will be coming as plus 18. So right is going to have a plus 18 microcoulomb. Right of C2 is going to have plus 18 microcoulomb. So option number B is the correct one. Option B is correct. Next question. It states that a parallel plate capacitor having a capacitance of 12 picofarad is charged by a battery to a potential difference of 10 volt between its plates. The charging battery is now disconnected and a porcelain slab of dielectric constant 6.5 is slipped between the plates. The work done by the capacitor on the slab is. And in this case, we are given that we have a parallel plate capacitor and its capacitance is, let us suppose, our C1 is our 12 picofarad and the potential difference, let us suppose, that is V1 is our 10 volt and it is connected to a battery. In the second part, the battery is removed and a dielectric is introduced between the plates. So, and dielectric is constant is given as K. So value of dielectric constant, that is K, is given to us as 6.5. And let us suppose the capacitance is now C2 and the voltage is suppose V2. But the charge on the first case is, let us suppose, that is of Q1, and the second case, let us suppose, that is Q2, which will be equal to our Q1, because charge will be, battery disconnected, so the charge is going to remain same. So we can find out easily our Q1. Q1 is equal to C1 V1, which is equal to 12 multiplied by 10, and this comes at 10 to the power minus 12. So we get our Q1 is equal to 1.2 into 10 to the power minus 10 coulombs. And new capacitance, that is our C2, when dielectric constant K is introduced, this is equal to K times C1. So this comes as 6.5 into 12 into 10 to the power minus 12. So we get the C2 will be equal to 78 into 10 to the power minus 12 farads. And we can easily find out our voltage because the charge is going to remain same. Therefore, we can say our V2 will be equal to our Q2 upon C2. Q2 is our Q1, which is our 1.8 into 10 to the power minus 10 divided by 78 into 10 to the power minus 12. So this gives us that our V2 will be equal to 1.5 538 volts. Now we can easily find out the initial as well as final energy. So initial energy, let us call this a U1, will be equal to over half C V square, and this comes as half C is our 12, 10 raised to power minus 12 multiplied by V square. V is our 10, so this comes at 10 raised to power whole square. So we get our U1 is equal to, this will be coming as 6 into 10 raised to power this will be 2 square, 10 raised to power 2 minus 10 joules. And similarly, we can find out our U2. Our U2 is equal to over half, and this comes as, capacitance was our C1, C1 and V1. This comes as C2 and V2 square. So this comes as half. C2 we found out is 78 into 10 raised to power minus 12. V2 is 1.538 and its whole square. So we get our U2 is approximately coming as 0.923 into 10 raised to power 10 joules, minus 10 joules. So we found out our U2 also. Now we can easily find out the work done by the capacitor. Work done by capacitor, that is our W, is equal to U initial minus U final, which is our U1 minus U2. So we get our work done will be equal to 6 minus 0.923 into 10 raised to power minus 10, which comes as 5.077 into 10 raised to power minus 10 joules. Or we can write this as work done is equal to 508 picojoules. So this comes as 508. Option B is correct. B is correct. So these were 12 questions asked in the 2019 mains, and this was the part 3 of the series of questions which were asked in the 2019 mains only. So we are also going to do part 4, which will be consisting of remaining mains question and advanced question from the year 2019. So this completes part 3. Thank you.